Hi, we're going to talk a little bit about pH right now. And here is a pH table with some foods on it. This is acid-base equilibria part 5. And I'm Ms. Bedrosian. And no, I don't suck lemons. But a lemon is about a 2 to 3 on the pH scale, by the way. Let's talk about what pH is. It's the negative log of the concentration of hydrogen ions. pOH is the negative log of the concentration of hydroxide ions. Not difficult. In any cup of water that you pick up, some of the water dissociates. And so you get the concentration of H plus and OH negative is 1 times 10 to the negative 7th molarity. Teeny tiny amount. pH plus pOH is equal to 14 because that comes out to 7 plus 7 if you work it out. And pKa, we can take the P of anything, is also equal to 14. pKw. So just let's go right to an example here. The pH of blood, no blood, is 7.41. And it never wavers, by the way. If you're alive, it's 7.41. Oh, my favorite vampire. He loves blood, too. He counts it all. The count. All right. So you need to find the pOH, the concentration of hydrogen ions and hydroxide ions. The first part is easy because you know the pH. pH plus pOH equals 14. So what's the pOH? That's obvious. This is an easy one. This is 6.59. Now the concentration of hydrogen ions and hydroxide ions. Let's take a look at that. This would be 1 times 10 to the negative 7.41 for hydrogen. And there's the answer. 3.89 times 10 to the negative 8th molarity. And here it is for hydroxide. 2.57 times 10 to the negative 7th molarity. Hey, is that an acid or a base? Not telling. Ka is the acid dissociation constant. And we usually write it like this. An acid in water yields hydronium ion plus the metal anion, aqueous. Ka is expressed like this. H2O would not be there because it's a liquid. Liquids and solids aren't part of the equilibrium constant. We can write this as this way as well. Usually I just write it as an H plus, but in reality it's an H3O plus, not 0. So, but when you're dealing with aqueous solutions, you have to look at what's actually there. That's the issue. Is it a strong acid? Is it a weak acid? What is it? So, for example, if we look at hydrochloric acid as an example, 1.0 molar hydrochloric acid is a strong acid. There's actually no HCl. It all dissociates, every single one of them. That's what makes it a strong acid. So when you put it in water, it's all dissociated. Now remember, water dissociates a teeny tiny bit as well. It's in water and water's dissociating too. So some water comes apart as well. However, it's such a tiny amount compared to the hydrochloric acid that we do not even have to take it into account. So, as an example, if I ask you to find the pH of 0.10 molar nitric acid, what would that be? And do I have to take water into account? Well, the H2O is tiny in comparison to the pH of this. So what is the pH of this? Did you figure it out? the pH is 1.0. The water is much smaller, so we don't even have to worry about that. However, if I asked you to find the pH of 1 times 10 to the negative 10th molarity HCl, this is different. Look at how tiny an amount that is. What is water's pH? It's in water. Do you remember? 1 times 10 to the negative 7th molarity. This concentration is much smaller than water. So this will be considered negligible. It will not count because it's way smaller than the water even. Therefore, what will the pH be? So the pH will be 7 from the water itself. And this is the end of part 5. And, oh, one bat flies into the steeple. Okay, that's the end of this one. Hi, we're going to talk a little bit about